Can you hear me?
Yep.
Okay, thanks.
We can hear you now.
A little bit of robot-y, but it might go away.
All right, yeah, it might be. Hold on.
It's gone. It's good.
Okay.
Okay. Hey, Johnny, do you know if you'll be able to present next Saturday?
Um, I'm not sure yet. Maybe
Okay.
I'll let you know. Sorry. Yeah.
Oh, no problem. Just wondering.
Yeah, I will at some point. I mean, I don't know if it's going to be next week though. I'm still kind of putting things together. I don't
Oh, okay.
like. I want to do a good job. I don't want to do a shitty job, and there's still like some things I need to like go over. So I have a feeling it's probably going to get postponed. But
Oh, that's okay. Yeah.
yeah,
If that's the case, though, we probably won't have a meeting next weekend, but we will the weekend after. Starting the subjects and stuff.
yeah, okay, that's fine. I'll let you know for sure in like a day or two.
Okay. Yeah. No rush or anything. Oh, it's already 3. We'll give it like a minute or two.
No trophy, huh?
Yeah, Trophy's not here.
Is he reading
Yeah,
math
he
books?
has his 20 PDFs open in his browser.
Hey, don't knock it till you try it. It's the only way I work.
I have quite a few PDFs open right now.
It's a pretty revolutionary way.
Yeah, to revolutionize the study of history.
Yeah, I think it's just because like we were having a conversation once and we're like, do you read any kind of novels? He's like, I don't really read anything except math books. I'm like, okay, that's good.
I'm just gonna let my phone charge.
He's min-maxing.
Yes.
What
He's
happened to
putting
your
all his
other account,
equipment.
Johnny?
Oh, well, I'm using this one because it's like less tied to like my personal identity, and not that like it's gonna really make a difference, but you know, in case I have wrong think,
Oh yeah.
Oh,
I don't know. I mean, I don't know what I'm doing yet in my life, but if I have to work, I don't know. I get a little paranoid with certain shit, but I I don't know. I mean, I don't know. I don't trust Discord. I don't think many people trust Discord, but
oh well, fair enough.
Alright. Well, I'm gonna. Is everyone ready? We can go ahead and start.
yeah.
Oh.
Yep. We're ready.
Okay. So before we start today, just wanted to say, as a reminder to everyone, we're gonna be studying some subjects up again here pretty soon. Um, the subjects that will be offered, materials and all of that will be offered for. The main one's homotopy theory. The other two are measure theory, so a first course in measure theory, and then the other one is differential topology. So let me just real quick talk about the prerequisites for those. Differential topology you have to have topology for. We won't be reviewing it. Things like maybe paracompactness, which do come up, the fundamental group, we might talk about. But in general, a good 1 or 2 semester undergraduate course in topology is required. Same for homotopy theory, but maybe a lighter introduction to topology course. Do you know what a Hausdorff space is? Those sorts of things that are kind of fundamental concepts. Be sure that you're okay with before we start. And then measure theory, as far as that subject goes, intro to analysis course. Maybe you went over a book in analysis if you read it and maybe did 3 or 4 exercises. That's kind of more than enough for the book that we're using. Typically people in this Discord will have some idea, some familiarity with the subject. So those sorts of things, that'll be sufficient. But we'll be starting that here in a couple weeks. So I think it's going to be the week of the 23rd. We'll have our first lecture on homotopy theory again. And, for more information about that, I've posted a link to the wiki that we'll be using to collaborate. Again, I encourage you to go check that out for more information about how we're going to be organizing each of the subjects. And of course, if you have any feedback, you feel free to let me know or anything like that. I would ask, if you think about, take some time to think about it. I would not recommend doing all 3 subjects at the same time, given the how much work is required for a subject on its own, But if you do come to a conclusion about what you would like to study, what you think you can handle, don't bite off more than you can chew. DM me what subjects you would like to do, or at me or something like that. That way I can kind of get a head count and an idea of what the groups are going to be. Okay, so again, smooth manifolds, differentiable manifolds, it's a full study. Measure theory, okay, and then of course homotopy theory. You don't have to do homotopy theory, you can do the other 2 or whatever order you like, but I would appreciate if you would, when you figured it out, take the time to let me know what you're interested in, okay? But nonetheless, today we're going to be talking about some Hodge theory. It's not going to be, you may have heard some buzzwords around the subject, partial differential equations, cohomology classes, these very big ideas that are usually not even touched on for undergraduates. We're going to be approaching the subject in a very light way today, and what I mean by that is we're going to be discussing some day 1 topics. So harmonic forms, Deramco homology, and then the famous Hodge theorem. Very fundamental concepts, almost day 1, okay, or the first month you take in an intro course to Hodge theory, you'll cover these things. Hodge theory, just to motivate it, it's an important subject for a number of reasons. It's really a marrying between algebraic geometry, okay, you have discussion of varieties and polynomials and all these things, and hardcore analysis. And the classic famous theorem that is the Hodge theorem really highlights that, because you have a linkage between homology and a space of harmonic forms. And harmonic forms themselves deal a lot with exterior calculus and differential geometry. And the proof of the Hodge theorem requires functional analysis and partial differential equations. If you're familiar with Sobolev spaces, that comes up in the proof. Not for uniqueness, but there's the existence part, which is where analysis comes in. So it's a very beautiful subject on its own. Different from geometric analysis in terms of what it's focused on. Hodge theory is more cohomology. Geometric analysis is going to be something where you're analyzing the geometry of Riemannian manifolds. Okay, but Hodge theory is great because you can extend a lot of concepts from differential topology to complex geometry. If you've read a book on complex differential topology, a lot of ideas from Hodge theory are essential to that analysis. But the first thing we're going to cover today, okay, you'll see the 3 subjects up there. You have forms, cohomology, and harmonicity. We're going to start with forms and bring everyone up to speed on what a form is. And we're also going to touch on tensors in a way that may seem a little bit different. We've kind of covered these topics before very loosely, but not with much motivation or an end goal in sight. But we will do so today. And forms, and you'll see how forms and tensors play with each other very intensely, and why why it's important that we talk about tensors in relation to forms. And it won't be in the algebraic sense. Okay, many of you will have seen forms in terms of fundamental property or whatever, where you say, okay, well, the space that exists in that commutative diagram, that's going to be the tensor product space. You may have seen it as, okay, well, the tensor product, that's just a quotient space. We're going to be introducing that a little bit differently. Our method for introducing the tensor product today is more differential topological than it is algebraic, but the properties that you get from the algebraic definition still hold, as you can verify. Some things that we will do today also, we're going to do some examples, some computational examples that you can take home with you if you want to maybe investigate this topic a little bit more. We're going to be covering a lot today nonetheless, so feel free to ask questions in VC text, and hopefully you find an enjoyment for this side of math. The first thing we're going to talk about is one forms. Let me get this up here. And really, it's a very easy concept. It's kind of hard to obfuscate it unless you really try. Take a finite dimensional vector space throughout this entire time. If there's a vector space, just finite dimensional. I know there's some issues that might come up if it's not. A one form is just a linear functional. And if you remember that, that's just a linear transformation that's real valued. Okay, so by linear, just to review, let me see if I can get my pen working. Okay, here we go. By linear transformation, okay, you can pull out scalars and vectors. So if I have omega of lambda v, v and w are vectors, we'll let the Greek letters be scalars. I can pull everything out, and that's going to be equal to lambda wv plus alpha w, omega of w. Okay, so that's a w, that's an omega. Okay, so it's just a linear functional. But there's a cool visualization for this. You may have seen this before. In a lot of physics books, enjoy introducing the idea of forms in this way, where you have a stack of planes and the value of your form, one form, or you're just linear functional, but we're just going to be fancy today, call them one forms for generalization purposes. The value of your, let's say your form omega at a vector, is how many times that vector v pierces this stack of hyperplanes in space. And just to explain the visual to you, let's just focus on this right here. Well, this visual is saying, and this doesn't really so much go fundamentally to our understanding of what we're talking about today, more than it is, if you see this visualization, you know what it's trying to say. These plates here, that's just the value of your linear functional, okay? The spacing is just visual, okay? Because in reality, there's infinitely many reals, and they're uncountably many, and they're dense in each other. So what you have is infinitely many planes here. And all this is saying is, what this is visualizing for you, when I input a vector, it outputs a real number, and that real number can be visualized as, okay, well, that vector, okay, pierces that number of planes. Okay, so in the case of v here, okay, v pierces 0, 1, 2, 3 planes. Okay, so the value of alpha at u would be 3. Okay, for a vector like w, it doesn't pierce any planes, so it just happens that so w is in the kernel of that linear functional. That's all the visual is saying in this case. Okay, just got to check VC text for those questions. Okay. In general, the construction of one forms on a manifold is a little bit different. For the time being, it's a little bit more intuitive if we focus on things in Rn for one forms, but really, putting this in the general environment, which is what we're going to try to do. The notion of when I talk about a differentiable manifold, I think for all simplicity, just think of a surface embedded in R2 and R3. Something that you've dealt with in multivariable calculus, not something like we're not going to deal with, one forms on the real projective space. Okay, so today when we talk about a manifold, kind of, go back to this rudimentary thinking of, okay, well, I just have some surface embedded in space where I can see it, okay? And so you have the intuitive idea of what a tangent plane is, okay? We're not going to go over the definition where it's an equivalence class. So what you have in general for a one form is that just as you can view here we go. just as you can view a vector field as a smooth section of the tangent bundle, there was a sci thread open a couple weeks ago that was talking about this idea. You know, what is a vector? And really, just to come, well, let's just start with this, just to cover the definitions. If I have a curve, okay, in R2, and you consider all the tangent vectors to that curve, okay, it's a parametrized curve. You know, I don't want to get pedantic, okay. You have all these different tangent vectors. If you put them all in the same set, okay, you take the disjoint union of all these tangent spaces, which is what they really are because these are all lines. Okay, well, these are all vector spaces of themselves. You take the disjoint union of all these vector spaces, you get the tangent bundle. Okay, and when I say take a smooth section, okay, that's just going to be technical terminology, but the product of taking a section of a tangent bundle is getting a vector field, okay, and so you might get something like this. Okay, well, this is a vector field right here. Vectors in space, vector fields that you dealt with in multivariable calculus, okay. So we know of a vector field as a smooth section of the tangent bundle. Now, you know, just as you have a vector space, you have a dual vector space. Okay, the dual of a vector space is the set of linear functionals on that vector space. So what you have here is a complete direct analog of a vector field, but for the dual space of the tangent bundle, okay, which is the cotangent bundle. And a section of that is a one form. That is the general definition for a smooth manifold. Okay, so you have that alpha is a one form if alpha is a mapping from the tangent bundle of M, so the set of all the disjoint union of all tangent spaces on your manifold, over to R, and then restricted to each point, alpha, your one form, becomes a linear functional on the tangent space at a point X. So you just have literally, here's, you know, the tangent space at a point X, and then you have alpha restricted to X, or alpha sub X, which is defined as alpha restricted to this specific tangent space. That goes over to the real line. Okay, so that's the general definition of a one form. I'm just showing you that it's not impervious to the development today, but just to let you know that the results we're covering are still general to a good extent here today. Okay. Any questions so far? Okay. We're going to stop because it's tensor time. Before we go on to 2, 3 P forms, it's actually nicer to view them as tensors. There's an advantage to doing that. Introducing tensors early, we can talk about the wedge product in terms of that. We talked about the wedge product last time with just vectors, but we can bump it up to forms in general. But we define this certain types of tensor really as a multilinear functional that takes P inputs from the side. Well, we'll just do this. If I take VO times W, finite dimensional vector spaces, a tensor here is a linear functional as we define it. A tensor, let's just call H, takes a vector from V, takes a vector from W, and outputs some real number. Okay, and so in terms of tensors as we want to define them, for our purposes today, we say that a P times covariant and a Q times contravariant tensor. Now, the names come from how they transform from under basis transformations. We're not going to deal with that today, but that's just where the name comes from. That tensor at a point X is a section of, right, we talked about what a section of a tangent bundle was, vector field, section of a cotangent bundle, one form. Now it's a section of this tensor product space, okay, where we get that a PQ tensor is a multilinear functional of one forms and vectors. How many vectors will it be? Well, how many tensor products are over here? Well, P. So it will be of P vectors and then of Q1 forms. And we have just a linear functional. So we input Q1 forms into it, Q many, and then we input P vectors, and then a PQ tensor, for short, will output us a scalar. Okay, there's an advantage of this, and that is, we can just say a one form is a 0, 1 tensor. It inputs a vector, and it outputs a scalar. It doesn't input any covectors. And, you can also, again, you can call a form a covector if you want, but it doesn't input any one forms. We just input covectors, and it outputs a scalar. In general, the notation, we can separate it. Okay, so here's the P1 forms. In the left slot, left big slot, and then we have the Q vectors. Okay, so that's just our general notation for a PQ tensor. We can add tensors intuitively. So if I have a PQ tensor and I want to add it to another PQ tensor, I get a PQ tensor. Okay, it doesn't change. You know, this here, just for short, this is called the valence. Okay, so the valence of a tensor would be P covariant and Q contravariant. Okay, so that's what, you know, the name for that article there is. But it's actually a very intuitive addition. Okay, you know, H plus J is just going to be H plus J evaluated. It's a very intuitive definition there, okay, for addition. Now, tensor multiplication, okay, so we have addition, but there's also multiplication. For one forms, we define it in this fashion. And that's really going to be enough for us to be able to understand the concepts today when we talk about taking the wedge product. When we deal with that, we're only going to deal with one forms. But if I want to take the tensor product of one forms, of linear functionals, okay, that's going to give me a 0, 2 tensor. Why is that? Because phi, okay, well, that is a one form, so it has one vector input. Psi, that also has one vector input. When I take the tensor product, okay, that's just the direct multiplication. We can do that because they output to the reals, they're real valued. And that becomes a 0, 2. A 0, 2 tensor. Okay, so that's a general rule for tensor multiplication on one forms, and also note that it is not commutative. Okay. We're not going to really cover the general multiplication. It gets kind of messy, and it would, you know, obfuscate the main point what we're getting at today. But in general, if I have a PQ tensor and an RS tensor, and I multiply them together via the tensor product, I just add the respective components in the parentheses, and I get a P plus R and a Q plus S tensor. Okay, so just fun fact in that case. As far as bases, if you want to, you know, we were talking about the tensor product space V O times W earlier today. In general, if I want to list the bases of a tensor product space, and this is just might be good to know, what you get is the permutations of all the bases in R3 with all of the bases in this space. Okay, so you would end up getting 9 basis vectors. You would have E1, you would have E1, you know, and so on. You would just permutate that, and you would end up with 9 basis elements in that case. Okay, so just kind of a short talk on basis in that case. When we talk about, you know, this notation here, which we'll discuss in a few, understand that that's going to be a basis of the space we're talking about. So just, you know, why I'm bringing up bases in this case, you're permuting all of the bases from the first space with the second space, and then you get the basis of the tensor product space. Okay, that's enough of tensors for now. Now we're going to talk about two forms. So we talked a few months ago about the wedge product. You may not remember. We're going to review it really quick. But this is actually a very cool product that they don't introduce typically in you know, public school. But what you get is, if I have, okay, let's say R2. If you take a vector U, and I take another vector V, U wedge V is the oriented parallelogram formed. By following U, okay, it's kind of a specific fashion, but it just the order does matter in the wedge product. It matters what orientation you give. But it gives you get an oriented parallelogram out of it. Okay, so that's what U wedge V is. Why that's important, you know, if you think about it in very simple terms, when you watched a construction of the integral of a function over an area from A to B, this was very much an oriented manifold. You can look at it generally that you were taking the integral over, right? I go from A and I go to B, because you cannot necessarily interchange the indices in your integral. So you can view this here as an integral over an oriented manifold a to b. So it has some sort of orientation. When we generalize that, okay, we're talking about a line segment that's oriented. The 2D version of an oriented line segment would be an oriented plane. And to construct an oriented plane, we use the wedge product of vectors. Okay. Now, what two forms are, you know, you can kind of think of this interestingly. We take these vectors, we take these, you could call them one-dimensional vectors, and it outputs a two-dimensional oriented plane. And likewise, you can take three vectors, you can take the wedge product of them, and you would get the oriented parallelopiped. Okay? So this same idea translates to forms. I take a one form, dx, and I wedge it with another one form, dy, and that gives me a two form. So two forms are of this form. If I take the wedge product of two one forms, I get two forms. Now, why are these, you know, you may be asking, why are these one forms? What is dx and what is dy? There's many interpretations of it. Okay, I think there was even a thread on Sci about it. There's many interpretations on how you can view them. A very elementary way to view them is that this dx is just the projection map from Rn, well, let's just do R3, or R2, to the x factor. Okay, so if I take dx evaluated at some vector 2, 1, that's going to return me the x component of that vector. So that would be 2. You can already see why these are linear transformations. And hence, well, not only linear transformations, linear functionals, and hence they're one forms. Okay, and so dy of this vector, dy of this is going to be what? Well, that's just going to be 1 because that's the y component. Very, very straightforward. So these are linear transformations, dx and dy, and hence they're one forms. Sorry, linear functionals. I mix those two up. Okay, and then when I take the wedge product of them, well, what does that do? And we're going to see in a minute, you know, what this is specifically defined as, but what it, in general, well, not in general, it does, it gives the area, the signed area, when I evaluate this at some vector, well, if I, one sec, let me write this correctly. That gives the signed area of this parallelogram. So that's what dx wedge dy does. It gives a signed area of the parallelogram. When I evaluate it two vectors, it gives me that area. Okay? But how do you define the wedge product on forms? If I, in general, if I just have forms, you know, they could be one forms, two forms, p forms, whatever. If I take, let me see if I can do this. Yeah. Come on. My pen doesn't want to work. Hold on. Oh, here we go. All right. If I want to take a form alpha, and we'll just go one forms for fun, and I take the wedge product with beta, that is equal to alpha tensor product with beta minus beta tensor product with alpha. And remember, these are not equal. And they're also not negatives of each other. It's not anti-commutative. It's not commutative. We just don't know the values that are different from them. So this is the definition of the wedge product of two forms. And so you may be asking, okay, well, why does that return the area? Because we want to know, because you know the area of that parallelogram would be the determinant of U1, U2, V1, V2. Okay, and so how do you pull that out of this? One second. Oh, sorry about that. I just got this weird email. Okay, how do you pull the signed area out of this tensor product expression? Well, I'll show you. It's very simple. So if I take dx wedge to y, evaluate it at, we'll just write the vectors out, u1, u2, and v1, v2. Okay, we just plug right into the definition. That's equal to dx tensor product with dy minus dy tensor product with dx. Okay. Again, evaluate it at the vector u1, u2, v1, v2. You may already be able to see what's happening here. When we evaluate this Okay, remember what the tensor product definition was. These are one forms. Okay, so when I evaluate this one form, we can split this subtraction up. When I evaluate this one form at these two vectors, that's going to be dx evaluated at u1, u2, and dy evaluated at v1, v2. Well, what's dx going to do? That's going to spit out the x component. Okay, so that's going to be u1 and then v2 minus, you can already see it coming, v1, u2. And that is the determinant of that matrix up there. Hence it gives area. So there you go. So that's, you can obviously see the interplay between the wedge product and tensors in this case, which is why it's such a useful way of putting things. Let me see what else we have coming up next. Okay. You know, there's a way of also looking at forms abstractly. Okay, so you can say that a 2 form, instead of looking at it as a wedge product, it's an antisymmetric 0-2 tensor. Okay, so if psi, capital Psi, is a 2 form, if I switch the order, I have to put a negative sign out front. Okay, and that's generally true. Excuse me. Common property of the exterior product is u wedged v is equal to negative v wedge u. And that makes sense geometrically. Okay, if we go back to this, if I reverse, if I instead of consider v wedge u, well, the orientation is going to go the other way. It's going to flip it. Okay, so a 2 form is an antisymmetric 0-2 tensor. That's where the intuition comes into the definition. And then a p form is a completely antisymmetric 0p tensor. Okay, so if I just keep, you know, if you want to not view this in terms of tensors and start viewing this in terms of wedge products, if I just take, you know, dx wedge dy will work in R3, wedge dz. Okay, well, that's a 3 form, and I can just keep doing that. But if you wanted to define it in terms of tensors, which can be helpful, it's just a completely antisymmetric 0p tensor. And if I swap any two of the vector inputs, okay, that are next to each other, that's going to reverse its sign. And I believe that's also equivalent to taking odd permutations of elements of the wedge product. I believe that's the same. But in general, you can view it as if you swap any two of the vector inputs, you're going to reverse the sign of your form. Okay? And remember that all forms are real valued as well. There's also complex forms as well, which will become useful once we talk about some later topics today. Now there's this idea of exterior differentiation. So you can differentiate a 1 form. Okay, well, that's a real value function. We know how to do that. If I take the derivative, okay, the exterior derivative of a 1 form, which is just a linear functional, that's going to give me the divergence of that. Very simple concept there, okay? And to generalize that further, we use the exterior derivative, okay? And the result, we get a p form, we plug it into the exterior derivative, and it outputs a p plus 1 form, so we move up. Contrary-wise, what will become important today is the transpose, or the adjoint of this. This is in fact a linear transformation, so we do have an adjoint, and the adjoint of that will help us construct the Laplace operator. But it may be helpful to see an example of the computation. It can be quite, I guess I would say, not very fun to do so, but I will just show you real quick. Well, let's see. Okay. Well, this would be nice. So let's just say in general, let's just keep it general for fun, that we have a 1 form that looks like this. Oops. I already messed that up. Omega is equal to f dx plus, and we'll say they're of 3 variables, so I won't write them out again, plus g dy plus h dz. If I wanted to write d omega, okay, using this definition, what's implied here, we're using the Einstein summation notation. So there's an implied sum across I up to the dimension, and there's an implied sum across capital I, which is a multi-index, which we don't have to deal with because this is a very simple example. But there's an implied summation across both of those. So what you end up getting is a double sum in this case. So we're summing across, well, up to the dimension, we'll have a double sum from 1 to 3. Okay, just given the simplicity of what we're working with. Just writing out the definition of the partial of the ith component here. Okay, so we'll say, actually we'll do partial omega I, partial xj. Okay, so x1 would be x, x2 would be y, x3 would be z. And then omega I, okay, omega 1 would be f, omega 2 would be g, etc., etc. Okay. And then you would do the wedge product, dxj. It's a very, very cumbersome computation. But what you get at the end is something that will look rather familiar, which is in fact equal to the del operator cross product with your omega. Okay. And what you get is something that's quite hefty. I don't know if it's, maybe it's not necessarily worth showing you. There's not too much that gets revealed in something like this. But I guess I'll write it anyway. You get quite a hefty term when you, I mean, actually I don't know if this is necessarily useful to anyone. If you get the idea of what the exterior derivative is trying to say, and this is probably better than doing an example computation right now. What it's generally saying, and what you have to take home from it, is that it's generalizing the notion of the derivative to vector calculus. And when you come across things like curl, the curl operator is just an exterior derivative. Okay, it is actually the Hodge star, which we'll talk about in a few. It is the Hodge star of the exterior derivative. Okay, so concepts like that generalize the notion of the exterior derivative. I'm sorry, the exterior derivative generalizes concepts like that. And that's all you need to know. There's not much use in doing the computation, but understanding what it is very important. And an important fact that, Abdul wrote out that you will see when you study differential topology is that if I take the exterior derivative of an exterior derivative, it's equal to 0. Okay, and that actually will come in a little bit useful later when we talk about Deramco homology. Okay, and here it is. If, there's these things called closed and exact forms, they're pretty interesting because we're about to relate the shape of a space to something that's very calculus-like, wedge products and oriented areas, and we're about to relate it to the topology of the space. So we say that a form is closed if its exterior derivative is 0. Okay, and then it's exact if it's the exterior derivative of a k-1 form. Okay, so an exact form can be produced by taking the exterior derivative of another form. Now, every exact form is closed. When you think about why, that's because if I have omega exact, back to what Abdul was saying, I can write omega as the exterior derivative of some other form. And again, because the exterior derivative composed with itself is 0, that implies that the exterior derivative of omega is 0. So every exact form is closed. This gives us an interesting symmetry. If you've studied this, when we talk about Deramco homology, you probably have seen this. We won't do examples. That's not necessarily enlightening. Because I hope, unless you guys want to see examples, I hope this definition is clear from what it's saying. We don't have to compute that something's closed necessarily. Okay. But what you might see here is, if you've seen the actually, I don't know if I want to spoil it right now. We'll wait. But what you get with this general thing is, this idea of forms in the exterior derivative. And it's kind of a pause here. This isn't essential to the development of what we're talking about. But what you get is the generalized Stokes theorem. And what it does is it relates the differential to the boundary in a very interesting way. What this is saying that, ignore these technical terms. We have an oriented, smooth manifold, okay, to the surface embedded in R3. Omega is compactly supported. You don't really need to know much about compact support. What you need to understand is this very simple formula that's very beautiful in terms of how it relates boundary and derivative. This is saying that the integral over your surface, integral of the exterior derivative of some form over your surface is equal to the integral over the boundary of that surface of the original form. Cool, I guess you might say, but how does this relate to what I already know? Think about it in calculus as if I take, if I say f is the antiderivative of little f, we just get the exact same thing. So M is our oriented manifold, that line segment. Okay. This is equal to it's kind of cumbersome notation to write all this out. Capital F. Okay. Well, df is just little f. Okay, we're saying that we just write little f as df. And then your integral over the boundary of your antiderivative, well, that is just equal to f of b minus f of a. And here you see why the Stokes theorem is a general form of the fundamental theorem of calculus. So not only have we generalized it to Rn, but we've generalized it to manifolds in general. Not essential to the development of the text, but I thought that while we were at it talking about forms, we might as well just take a stop at this theorem because it is pretty interesting. Okay, and we don't really need to do examples. Might take some time. Okay, but now we're at the essential topic, which is Deramco homology. And what's important to see here is that we take, well, let's see how I would like to introduce this. Oh, you know what? Maybe it would be probably best if I think we'll do this first. Let's talk about a little bit about the idea of just homology in general. Or, no, you know what? We'll introduce the definition. It's probably better. What Deramco homology gives us is yet another way, okay, the idea of homology, the motivation from it, was if I have a topological space, I want to know how many holes are in it. Okay, that is important for numerous things if you've done complex analysis, and it's important for integration and residue calculus and all these sorts of things, all these fancy terms. But it gives us this notion of shape. In Deramco homology is another way that will tell us how many holes are in our space. And for differentiable manifolds, or smooth manifolds, it's an optimal way of doing it because we have a notion of a tangent space, we have a notion of forms on manifolds, and so we utilize that, okay, to build the Deramco homology group. Okay? So a couple things to think about. Well, I'll just put this fact here just so we have. That exterior derivative, that's linear, okay? And that's just going to explain why the following are vector spaces, okay? Define the set Z, and this notation is not on accident, by the way. It'll be very familiar if you've taken algebraic topology. Define Z P of M. That is going to be equal to the set of P forms that are exact. And maybe some notation. The set of P forms on a manifold is denoted this way. Okay. Oh, sorry, not exact. Closed. I already messed that up. Are closed. Okay. So if its derivative is equal to 0, it's in ZP. And we're just talking about general P forms now. Now B, okay, well, we talked about closed form. It's going to be the P forms that are exact. Okay, and if you've seen homology before, you can probably guess what I'm going to define now as the Deramco homology group. The Pth Deramco homology group for P forms, because we have a different group for one forms, two forms, just as in homology we have different homology groups for one simplices and two simplices and those things. That is the quotient space, because these are actually indeed vector spaces. That's the point of me stating that D is a linear operator. Okay, these are vector spaces. So we have this notion of a quotient vector space. And we call this quotient vector space the Deramco homology group in degree P, or the Pth Deram group, whatever you like. Okay, we haven't really seen why this is quite important yet. We've just defined this quotient space with familiar notation, with the familiar inclusion here, which is every single exact form is closed. So B is a subset of Z. I don't think I have that backwards. Let me just make sure. Oh, I don't think I have that backwards, right? Yeah,
I'm sorry.
Form is closed. Yeah.
Sorry for interrupting you. I just
Oh, go ahead.
think. What was B again? I couldn't.
Oh, B is the set of P forms that are exact. And what I mean by exact, they can be expressed as the exterior derivative of another differential form.
Oh, you defined it this way and then you call it B. Or maybe I'm
sorry, I don't know what it's hard to hear you. What's your question?
yeah. Okay. I think I get it. This is a definition.
Yeah, this is just a definition.
And you just like named it.
Yep, I just named it. Yep.
Yeah, okay. Sorry.
No, you're fine. Okay. Okay, so now we have the Duran cohomology group. It's pretty interesting because we took a quotient space of a couple things. It looks familiar. If you remember, this set inclusion in homology theory, and I don't think we'll necessarily go over homology theory today. What you want to know about it is that your pth homology group of your space is usually denoted something like this. No, it's not R, it's Z. Okay, the dimension of this, and this is a vector space, the dimension of your homology group, that is equal to the number of holes in M. Okay, and the Durham Theorem states that the Deramco Homology group, the pth one, is in fact isomorphic to, this is a big deal, to your regular homology group. That's what the Duran Theorem states. So I don't have to deal with triangulations of my surface whatsoever to figure out how many holes it has at all. I just need to compute the Deramco homology group, which is more optimal if my surface is differentiable. That's fantastic. And that tells us where the fundamental calculus fails to hold, or Stokes theorem also, you'll call it that. Yeah, Stokes theorem, where that fails to hold. It tells you where the holes are in your space. So necessarily the dimension of your Deramco homology group is also equal to the number of holes. Very, very nice result for something like that. Okay, so that gives us yet another way to compute holes in your space. It gets even better in that case. And this is where we'll start to come to the, I guess you would say, the best part of this whole thing, which is harmonic forms. There is yet another way to determine how many holes a differentiable manifold has. And not only that, because here we're just talking about smooth manifolds. And those charts, okay, the charts for your smooth manifolds are real valued. What's great about the generalization we're about to make is that we can use a different type of forms. And this is why it's important to talk about this today, the motivation here, where you can use a different type of forms that work very well and very intuitively in the complex vector space. And for complex manifolds, that will tell us how many holes we have in our complex manifolds. Okay. So now that we have Deramco homology down, it's isomorphic to something very nice. It's a very nice isomorphism. It's the homology group. Now we're going to talk about something that's also isomorphic in and of itself to the Deramco homology group. Okay. Let me just pull this up real quick just for reference. I don't want to get this wrong because it's pretty cool. When I was talking about the Hodge star earlier, it's sort of, the definition, if I were to introduce it and we were to talk about it, we would probably get lost in the weeds and maybe lose sight of what's great about harmonic forms and where Hodge theory is really taking us. What I want you to think about is kind of the following computations. You may not get necessarily the best feeling for the Hodge star just from these computations, but it'll at least, tell you how you might work with it in the wild. Let me see if I can. Right, hold on. There we go. All right. So if I have a form, and this is a one form, phi, we'll just say a dx plus b dy. I don't think it would be too nice to do dz. The Hodge star of phi is going to be equal to Well, let me see. Actually, no, we should do dz. That would probably just help. The Hodge star of that is equal. Well, no, that's not really useful. I'm trying to think of a good, useful way to talk about this in a quick manner. Sorry, one moment. Okay, well, this is actually good. In a way, you can think about it as you put in a form, and it outputs the orthogonal form. Somewhat, that's an incorrect definition, but it does still kind of hold in the computation. Okay, so if the Hodge star for the form dx, okay, you can think about this very intuitively. In R2, our basis vectors for the space of one forms are dx and dy. Okay, what's orthogonal to the x-axis? You have the y-axis. What's going to be orthogonal to the dx form axis? It's going to be the dy form axis. Okay. But to go backwards, okay, when I take the Hodge star of dy, that's going to spit out negative dx, because the way that we are talking about orthogonal is consistent. Okay, so dy is left orthogonal to dx. Okay, and that makes sense. I go this way, but dy is right orthogonal to dx, so I go this way. It's a very loose way of talking about the Hodge star, but you think about it in orthogonality, and it might make a little bit more sense. Okay. So this is how the Hodge star acts in this case, okay? And when we talk about the exterior derivative, we want to talk about, I just lost it again, the transpose, I always forget what this word is, adjoint. And we want to talk about the adjoint of the exterior derivative. We can express it using the Hodge star in this fashion. So this is the adjoint, and you may also see it written of D. Okay, so that's the adjoint D star of D. So Hodge star D, Hodge star. Okay, and you can take the exterior derivative of the Hodge star operator. Not necessarily enlightening today, because I want to get to harmonic forms as fast as possible. But just to kind of give you some sense of intuition about the Hodge star, I would highly recommend you take the time to go look up about it and get comfortable with the intuition. Why do we care about the Hodge star? Why is it defined the way it is? But I think orthogonal complements is good enough. Okay, so you can think of this adjoint of the exterior derivative. When you define it in terms of the Hodge star, you can think adjoint, okay, transpose complex conjugate as well. When you're dealing with complex matrices, you have this notion of transpose and maybe, the orthogonal space, the orthogonal matrix or whatever, okay, in that sort of sense. So look at D star as kind of the somewhat opposite of D in a sense, not that it's an inverse. I know this is, a very bad explanation for the Hodge star, but you have D star as the adjoint of D. And the importance of defining the adjoint of D is that it allows us to define the Laplacian for harmonic forms. So we know what the, let me see, I should probably create another, here we go. I'm going to create some more slides here real quick so we can talk about this. I did not expect to need this much space, but okay. Okay, this is great. Okay, let's go all the way through again. I'll start presentation from here. Okay, well, just sorry about this. I don't know why it's okay. This is great. All right, let's just look for something that's blank. Okay. When we define the Laplace operator for functions, okay, we have this idea of what a harmonic function is if you've taken complex analysis. If I have a real valued function f, okay, or a vector valued function, whatever, the Laplacian of f is the sum of its partial derivatives, okay? So you get partial f, partial xi. You take the sum of those, xi, I guess you would say squared. Okay. You take the sum of those. This is also the trace of the Hessian, for those of you who are familiar with the Hessian. And that's the Laplacian of f. We talked about this I believe last weekend or the weekend before about, if it happens to be that the Laplacian of a function is equal to 0, that means we say that f is harmonic. Okay, and what happens when we have a harmonic function? Well, a lot of things open up. The values of f are now the the value of the average value of f in a ball or a ring around f. Very nice. A lot of things, we can now represent harmonic functions. If we know the values of a harmonic function on the boundary of a closed domain, we can actually determine, using a representation formula, the values of that harmonic function inside the domain. Okay, so I can express a harmonic function in terms of its values on the boundary. Very great properties of harmonic functions. Those don't necessarily carry over to forms, but we still get a powerful field of theorems and concepts when we talk about a harmonic form. So for forms, this is functions. Okay, now for forms, the Laplace operator is equal to the adjoint of the exterior derivative. You can also call this the coderivative of the exterior derivative. So the coderivative of the exterior derivative of your form is the Laplacian of that form. There is no use today going through a computation of this. It is incredibly messy. I spent the week trying to get a nice one down. That may be me obfuscating things. It's a very messy computation to determine the Laplacian of the operator. You're much better off just, trying to weed your way around doing an explicit computation. Okay, but what's important here is that when we get down to zero forms, this works for all forms, meaning for zero forms, which are just scalars, okay, and when we get down just to functions, this actually will return the usual definition of the Laplacian, okay, because of the nature of a function. When you do go through the computation, you actually return the regular Laplace equation. Okay, so this is a consistent definition, and it is indeed a more general definition. So it is indeed generalizing this notion of harmonicity to forms. Okay, now a form, we'll say a P form, omega is harmonic, no surprise here, if its Laplacian is equal to 0. Now what happens here is the climax of this talk today. What happens when this occurs? When we have harmonic forms introduced to differential topology? Well, we have a couple things. And one of those things is, maybe, can I get another blank slide? Oh, perfect. Another thing is that every cohomology class, and we'll talk about what a cohomology class is, contains a harmonic form. It's an existence theorem. This is what is known as the Hodge Theorem. Okay, so let me write this, if I can get writing. This is called the Hodge Theorem, and this is one of the principal results of Hodge theory. This is as important to the subject as the fundamental theorem of calculus would be to calculus. Okay, so we're going to work in the space of P forms on a differentiable manifold, surface embedded in R3 if you like, Rn or whatever. Okay. Alpha and beta, all of our forms are going to be closed, so alpha and beta are closed. Those two forms are called cohomologous if alpha minus beta is exact. Okay? And from this, you can get an equivalence class very easily. Okay? So you can define an equivalence class alpha. So those are all forms omega such that omega minus alpha is exact. Pretty simple. Okay? And the set of equivalence classes, the set of such equivalence classes, if you remember the quotient space definition, that is literally the Deramco Homology group on your space. It's just that we just restated things, but now we just have this cohomologous definition. What the Hodge theorem says is that, well, let me get another blank slide. I don't know if we have any more. Oh, that's great. We're kind of all over the place. Let me see. Okay. Come on. Oh, my pen's doing the same thing again. Just give me 1 second. Oh man, am I gonna have to write this out? Just give me 1 second. Oh, finally. Okay. What the Hodge theorem says is let M be a, we'll say, nice manifold. And by nice, I mean it's compact and it's Riemannian. Now, let's explain Riemannian for a second. It's important to the proof, but you can still see the beauty of the result without understanding what a Riemannian manifold quite is. Okay. A Riemannian manifold, what you do is you take a differentiable manifold and you equip it with an inner product at each point. Okay, and that inner product's on the tangent space at that point. Okay, so think manifold at its very basic. Think a differentiable smooth manifold, surface embedded in R3 if you like, and every point has a dot product function defined on it. Okay, for the tangent vectors originating from that point. Okay, so it's a compact, closed and bounded, if you like, Riemannian manifold. Then what the Hodge theorem says, this is so cool, every cohomology class contains one unique harmonic form. Isn't that interesting? Any cohomology class, okay, in the Deramco Homology group contains one form that is harmonic. Pretty interesting. Not only that, but maybe even the sweeter part for you is that the space H delta P, which is defined as the space of harmonic P forms on your manifold M, under the right conditions, is isomorphic to your Deramco homology group. And yet here we have another way of finding out how many holes our space has. If you don't want to deal with Deramco homology, you can deal with harmonic forms. Well, let's start from the beginning. If you don't want to deal with homology, you can deal with Deramco homology. If you don't want to deal with that, you can deal with harmonic forms. And what's great about this definition is that it transports wonderfully, as you may have seen, harmonic functions discussed in their entirety in the first time in complex analysis. This translates wonderfully to complex manifolds, which is what makes this result so nice. Now, the proof of this result is quite extensive. The uniqueness portion is not very difficult for this first result. The uniqueness is not much. You just assume there's two that satisfy the same condition, and then you prove that, okay, they must be equal. It's actually a very simple result. The existence, let me actually, because I wrote down what you need. The existence of it is quite astonishing. You need the Sobolev norm for Sobolev spaces. You need lots of topology. You need the L2 norm, so you need some measure theory. You need some Riemannian geometry in there. It's a amazing result that even Hodge himself called when he was trying to prove it. It's a monster. It's a monster of a proof. I encourage you to look at it. Trying to think of some books that have a proof on it. There's a great book by Jürgen Jost on geometric analysis, and he lays out this proof if you're interested. But it is quite the result, and it is a fundamental result in Hodge theory. There's much more beautiful results, but they can all build off this one. And so this is a very just light glimpse at what the subject discusses. And so there you have it. That was the result that I was intending to build to today. So in that, the talk is complete. So I hope you guys enjoyed. Thank you all for showing up and listening and watching. So I hope you enjoyed it. I hope you enjoyed, getting some intuition on differential forms. But if you have any questions, though, I'd be happy to take them.
Yeah, can you go back to the slide where you define the cohomology group? I think I maybe mixing up closed and exact forms.
Yep.
So
It's closed over exact.
okay, closed
So,
over.
think about it. Closed is a lighter condition than exact. I guess exact is a lot harder to prove than closed because you have to work backwards. But yeah, closed forms over exact forms for your Deramco homology group.
Got it. So then,
That tells you how many holes you have in the space, and that's by the Duran Theorem, which is a Deramco homology group is isomorphic to the Pth homology group. There.
okay.
And we will also, if you do study differential topology, when we start, we'll reach the Duran Theorem. So this will be covered again as well, if you were interested in what was talked about today. Also, some books. If you did find this interesting, and you would like to know a book, what you can look at. One that has a nice introduction. Know a little bit about homology. Know a little bit. You need topology down. Know a little bit about complex analysis. There's it's kind of a famous book almost by Voisin. That is Hodge Theory and Complex Algebraic Geometry. It would be very nice if you read the first few chapters of Lee. Okay, that would be great because he starts off with complex manifolds. But if you're interested in this, because this is why I used to prepare a lot for this one. In addition to Yost's book, very good book on the subject. There's also some lectures online about it as well. I believe ICTP, or I think it's a Portuguese lecture program. They have lectures that use this book. Okay, so I would if you're interested, I implore you to investigate that. So, okay.
Actually, I was wondering, don't you need like normal algebraic geometry for this book? Because I've heard of it, I've seen it, and I was always like taken aback or like being scared of it because algebraic geometry, oh, so scary, right?
Yeah, I think what makes Hodge theory, and this is just from what I've read, the approach to Hodge theory is going to be a lot different to algebraic geometry. So with Hodge theory, you don't need to know about varieties for quite a long time. And in fact, you can study Hodge theory and avoid varieties, and avoid categories for a good like if you're not interested in Grassmannian stuff and those categories and projective varieties and all of that, you can study Hodge theory. You can do an intro course that really brings together algebraic geometry. So if you don't necessarily need to worry about, because the book is Hodge theory and complex algebraic geometry, you can do the complex topology part, and when you get to the algebraic geometry stop, you can. But the book is written, I would say, more than not accessible to the subject. There's also some other good ones. I would say if you want a no algebraic introduction to Hodge theory, Riemannian geometry and geometric analysis is great. Okay, you'll get up to speed on harmonic forms. You'll talk about harmonic maps between manifolds. Okay, specific more so to Riemannian geometry, but still you're using Hodge theory concepts. So you're not losing sight of things. You talk about floor homology. There's still homology theory. There's still algebraic topology, and I'll just write that here. This is a great book. I would vouch for it. Riemannian geometry and geometric analysis. Okay, so if you want a more analytical, and I would heavily recommend analysis, you got to know measure theory. You have to know what a Sobolev space is. Know some results about elliptic partial differential equations. The prerequisites for both subjects are quite large. That's why they're. Oh, did I spell misspell? Thank you. Okay, I thought I did. I didn't think there was an O there, but yeah, Voisin. I mean, both subjects. You need You need a pretty hefty background to study them. So I would recommend, if you want a lighter introduction that doesn't necessarily it because he talks to you about tangent spaces, he brings you up to speed on those in the first chapter and has exercises on those. Jürgen Jost will be a lighter introduction, still heavy. Nonetheless, it's a challenging book. But Voisin, if you're up to it, that will be focused more on the Hodge theory side of things. So, yeah.
Yeah. Thanks, though.
No problem. You guys got any other questions? No, I don't know. I have not studied cobordism at all. At all. I don't even know what it is. I know it's in Milnor. I don't think even Lee talks about it in his differential topology book. No, I don't know anything about bordism. Which might be bad. I don't know how essential that is as a subject. Like, I also don't know anything about Morse theory. Well, okay, maybe little. Maybe, I mean, I know the what it's trying to get at. And there's some interactions with. I don't know. I guess I have like a meme, a pop sci understanding of that. So I cannot recommend you any books. I think Milnor. I was watching a conversation. I think it was Milnor or Spivak, something like would probably be more Spivak than. One of those two wrote a book about it. Is the point I'm making. So Milnor. Okay, yeah. So it's Milnor. Yeah. Yeah. Okay. Any other questions? Okay. I will post. I don't know how useful these annotations are, to be quite honest with you, but I will definitely post the video. I want to edit out some parts, but I will post the video to YouTube if you want to go back and look at this lecture. And then also with that, be sure to reply. Shancy's just put something in the chat. Be sure to reply to that. React with what you're interested in. So.
Yeah, I'll manually assign roles to anybody that does that within